Because of the central role that the Gaussian distribution plays also in finance, we will analyze its properties in some detail. Let's now describe some properties of the normal cumulative distribution function, normcdf. Consider a random variable capital X that follows a normal distribution of parameters mu and sigma. The normcdf is a real-valued function, usually denoted by capital Phi, whose arguments are a real-valued variable, lowercase x, mu, the mean, and sigma, the standard deviation. This function gives us the probability that a realization of the random variable is below or equal to lowercase x. If the values of mu and sigma are not specified, we will assume that the value of mu is 0 and the value of sigma is 1. Here on the left-hand side we have a plot of the normcdf, and on the lower part its relation to the normpdf. The parameters are mu equal 4 and sigma equal 2. At minus infinity, the normcdf has value 0, then it increases monotonically. By symmetry, it will take a value 1/2 at mu. It continues increasing monotonically until asymptotically it will reach 1 when x goes to infinity. Let's try to understand what is the value of phi, for instance here at mu minus sigma. This number here gives us the probability that a realization of the random variable is below or equal to that value. In terms of the PDF, it will give us the area that is underneath the curve between minus infinity and mu minus sigma. There are some probabilities that are interesting that can be computed in terms of this normcdf. For instance, consider P of alpha, which is the probability that a realization of the random variable is smaller or equal than mu plus alpha sigma. This probability can be shown to be equal to phi of alpha, where the dependence on mu and sigma drops out. Consider, for instance, alpha equal 3. So the probability that a realization of the random variable is below mu plus 3 standard deviations is relatively large, is 99.87%. And assume that you're performing experiments and that your null hypothesis is that the result of the experiment is a random variable that is centered around mu with a standard deviation sigma. What happens if the result is outside this interval? Well, you could obtain that result by chance, and the probabilities of obtaining it by chance is, on average, once in 741 measurements. Now, this 3 sigma result gives evidence that something is different from what you have assumed. That is not very likely to see this anomalous result. Let's compute the same quantity for alpha equal 5. The probability of observing a result which is below mu plus 5 sigma is very, very close to 1. It's 99.99997%. Assume now that you are outside of this interval, so you obtain a result which is beyond mu plus 5 sigma. Well, this would happen by chance once in every 3.5 million experiments. So this 5 sigma result would actually consist in a discovery. Something is definitely different from what you have assumed. In particular, your hypothesis that the results would be centered around mu with a standard deviation sigma is probably incorrect. That means that you have discovered something new. This is what particle physicists use to determine whether they have found a new particle in an experiment or not.